In this video, I'll be solving problem 10.11 from Taylor's Classical Mechanics. It asks in part A for us to use the result of problem 10.4 to find the moment of inertia of a uniform solid sphere, mass m, radius r, for rotation about a diameter. So the result of 10.4 is there. It's simply the integral of a function of position over a volume in spherical coordinates. So for simplicity, let's find the moment of inertia about the z-axis. The moment of inertia will be the integral of, let's use rho squared dm, where rho is the distance from the z-axis and dm is a tiny piece of mass. Since this is a uniform solid sphere, we can express dm as a density times a tiny bit of volume. And I'm using two different rows here. This one is the density. So first, how can we express rho, the distance from the z-axis? If we consider some point on the sphere there, then in spherical coordinates, it has a distance from the origin and it has an angle theta here. So we can say that rho equals r sine theta. Okay, then we'll set it up as a spherical integral. So pulling the density out in front, we'll have the density times r squared dr times sine theta d theta times d phi times the actual function, which, as you recall, is rho squared, which means it's r squared sine theta squared. The limits of integration, because this is a sphere, are in phi 0 to 2 pi, in theta 0 to pi, and in r 0 to capital R. So let's first pull out the phi integral. Since there's no function of phi, it just becomes a constant 2 pi out front. Let's do the r integral. Combining the r's, we have r to the 4th dr, which integrates to r to the 5th over 5, since we're integrating from 0 to capital R. And then we're just left with the integral from 0 to pi of sine cubed of theta d theta. So I looked up this integral, and you can too. It integrates to, just writing this out front first, negative 3 cosine theta over 4 plus cosine of 3 theta over 12. And that is evaluated from 0 to pi. Cosine is not 0 at either of those places. So we have 2 pi rho r to the 5th over 5 times negative 3 times the cosine of pi is negative 1 over 4 plus the cosine of 3 pi is also negative 1 over 12, and then we're subtracting a negative 3 times the cosine of 0, which is 1 over 4, plus the cosine of 3 times 0, which is 0, is 1 over 12. So this is equal to 4/3. So the moment of inertia is 2 pi r to the 5th over 5 times 4/3 times rho, the density, which is equal to m over 4/3 pi r cubed. Canceling, we have that the moment of inertia about z is 2/5 mr squared, which you might remember from looking at a table of moments of inertia freshman year. Part B, do the same for a uniform hollow sphere whose inner and outer radii are a and b. One slick way to do this is to think of the hollow sphere as a solid sphere of radius b from which you have removed a sphere of the same density, but radius a. So for part B, we'll do almost the same thing. We first will note that the volume will be 4/3 pi b cubed minus 4/3 pi a cubed, or 4/3 pi e cubed minus a cubed. We'll then do the same integral r squared dr sine theta d theta d phi r squared sine squared theta, but with slightly different limits of integration. Phi will still be from 0 to 2 pi, theta will be from 0 to pi, but r will only be from a to b. That's the thickness of the shell. So our result will be 2/5 e to the 5th minus a to the 5th over b cubed minus a cubed.